This lecture is about how we can evaluate a ranked list. In this lecture, we will continue the discussion of evaluation. In particular, we're going to look at how we can evaluate a ranked list of results. In the previous lecture, we talked about precision and recall. These are the two basic measures for quantitatively measuring the performance of a search result. But as we talked about ranking before, we framed the text retrieval problem as a ranking problem. So we also need to evaluate the quality of a ranked list. How can we use precision and recall to evaluate a ranked list? Well, naturally, we have to look at the precision and recall at different cutoffs, because in the end, the approximation of relevant document set given by a ranked list is determined by where the user stops browsing, right? If we assume the user sequentially browses the list of results, the user would stop at some point, and that point would determine the set. And then that's the most important cutoff that we'll have to consider when we compute the precision and recall. Without knowing where exactly the user would stop, then we'll have to consider all the positions where the user could stop. So let's look at these positions. Look at this slide, and then let's look at the what if the user stops at the first document? What's the precision and recall at this point? What do you think? Well, it's easy to see that this document is relevant, so the precision is 1 out of 1. We have got one document and that's relevant. What about the recall? Well, note that we assume that there are 10 relevant documents for this query in the collection. So it's 1 out of 10. What if the user stops at the second position? Top 2. Well, the precision is the same, 100%, 2 out of 2, and the recall is 2 out of 10. What if the user stops at the third position? Well, this is interesting, because in this case, we have not got any additional relevant document, so the recall doesn't change. But the precision is lower because we've got a non-relevant one. So what's exactly the precision? Well, it's 2 out of 3, right? And the recall is the same, 2 out of 10. So when would we see another point where the recall would be different? Now, if you look down the list, well, it won't happen until we have seen another relevant document, in this case, D5. At that point, the recall is increased to 3 out of 10, and the precision is 3 out of 5. So you can see, if we keep doing this, we can also get to D8, and then we will have a precision of 4 out of 8, because there are 8 documents and 4 of them are relevant, and the recall is 4 out of 10. Now, when can we get a recall of 5 out of 10? Well, in this list, we don't have it. So we have to go down on the list. We don't know where it is. But as a convenience, we often assume that the precision is 0 at all the precision is 0 at all the other levels of recall that are beyond the search results. So of course, this is a pessimistic assumption. The actual precision would be higher, but we may make this assumption in order to have an easy way to compute another measure called average precision that we'll discuss later. Now, I should also say, now here you see we make these assumptions that are clearly not accurate, but this is usually okay for the purpose of comparing two text retrieval methods. And this is for the relative comparison. So it's okay if the actual measure or actual number deviates a little bit from the true number, as long as the deviation is not biased toward any particular retrieval method. We are okay. We can still accurately tell which method works better. And this is an important point to keep in mind. When you compare different algorithms, the key is to avoid any bias toward each method. And as long as you can avoid that, it's okay if you do transformation of these measures in any way. so you can preserve the order. Okay, so we just talked about that. We can get a lot of precision recall numbers at different positions. So now you can imagine we can plot a curve. And this just shows on the x-axis, we show the recalls. And on the y-axis, we show the precision. So the precision levels are marked as 0.1, 0.2, 0.3, and 1.0. Right? So this is the different levels of recall. And the y-axis also has different marks. That's for precision. So we plotted these precision recall numbers that we have got as points on this picture. Now we can further link these points to form a curve. As you see, we assumed all the other precision that are high level recalls to be 0. And that's why they are down here. Right? So they are all 0. And the actual curve probably will be something like this. But as we just discussed, it doesn't matter that much for comparing two methods, because this will be underestimated for all the methods. Okay, so now that we have this precision recall curve, how can we compare two ranked lists? Right, so that means we have to compare two PR curves. And here I show two cases where system A is shown in red, system B is shown in blue with crosses. Right, so which one is better? I hope you can see, well, system A is clearly better. Why? Because for the same level of recall, let's see, same level of recall here, and you can see the precision point by system A is better than system B. So there's no question. Indeed, you can imagine what does the curve look like for an ideal search system. Well, it has to have perfect precision at all the recall points, so it has to be this line. That would be the ideal system. In general, the higher the curve is, the better, right? The problem is that we might see a case like this. This actually happens often. Like the two curves cross each other. Now in this case, which one is better? What do you think? Now this is a real problem that you actually might face. Suppose you build a search engine and you have an old algorithm that's shown here in blue, or system B, and you have come up with a new idea and you test it, and the results are shown in red, curve A. Now your question is your new method better than the old method? Or more practically, do you have to replace the algorithm that you are already using in your search engine with another new algorithm? So should we use method A to replace method B? This is going to be a real decision that you have to make. If you make the replacement, the search engine would behave like system A here. Whereas if you don't do that, it will be like a system B. So what do you do? Now, if you want to spend more time to think about this, pause the video. And it's actually very useful to think about that. As I said, it's a real decision that you have to make if you are building your own search engine, or if you are working for a company that cares about the search. Now, if you have thought about this for a moment, you might realize that, well, in this case, it's hard to say. You know, some users might like a system A, some users might like system B. So what's the difference here? Well, the difference is just that, you know, in the low level of recall in this region, system B is better. There's higher precision. But in high recall region, system A is better. Now, so that also means it depends on whether the user cares about the high recall or low recall, but high precision. And you can imagine if someone is just going to check out what's happening today and you want to find some relevant news, well, which one is better? What do you think? In this case, clearly system B is better because the user is unlikely examining a lot of results. The user doesn't care about high recall. On the other hand, if you think about a case where a user is doing, let's say, literature survey, you are starting a problem. You want to find whether your idea has been studied before. In that case, you emphasize high recall. So you want to see as many relevant documents as possible. Therefore, you might favor system A. So that means which one is better actually depends on users, and more precisely, users' task. So this means you may not necessarily be able to come up with one number that would accurately depict the performance. You have to look at the overall picture. Yet, as I said, when you have a practical decision to make whether you replace the algorithm with another, then you may have to actually come up with a single number to quantify each method. Or when we compare many different methods in research, ideally we have one number to compare them with, so that we can easily make a lot of comparisons. So for all these reasons, it's desirable to have one single number to measure that. So how do we do that? And that needs a number to summarize the ranking. So here again, it's the precision recall curve, right? And one way to summarize this whole ranked list or this whole curve is look at the area underneath the curve, right? So this is one way to measure that. There are other ways to measure that, but it just turns out that this particular way of measuring it has been very popular and has been used since a long time ago for text retrieval evaluation. And this is basically computed in this way, and it's called average precision. Basically, we're going to take a look at every different recall point, and then look at the precision. So we know, this is one precision, and this is another with a different recall. Now this, we don't count this one because the recall level is the same. And we're going to then look at this number, and that's the precision at a different recall level, etc. So we have all these, added up. These are the precisions at the different points, corresponding to retrieving the first relevant document, the second, and then the third, the fourth, etc. Now we missed many relevant documents, so in all those cases, we just assume that they have 0 precisions. And then finally, we take the average. So we divide it by 10, and which is the total number of relevant documents in the collection. Note that here, we're not dividing this sum by 4, which is the number of retrieved relevant documents. Now imagine if I divide by 4, what would happen? Now think about this for a moment. It's a common mistake that people sometimes overlook. Right? So if you divide this by 4, it's actually not very good. In fact, you are favoring a system that would retrieve very few relevant documents, as in that case, the denominator would be very small. So this would be not a good measure. So note that this denominator is 10, the total number of relevant documents. And this will basically compute the area underneath the curve. And this is the standard method used for evaluating a ranked list. Note that it actually combines recall and precision. But first, we have precision numbers here. But second, we also consider recall, because if you missed many, there will be many zeros here. So it combines precision and recall. And furthermore, you can see this measure is sensitive to a small change of a position of a relevant document. Let's say if I move this relevant document up a little bit, now it would increase this average precision. Whereas if I move any relevant document down, let's say I move this relevant document down, then it would decrease the average precision. So this is very good because it's very sensitive to the ranking of every relevant document. It can tell small differences between two ranked lists. And that's what we want. Sometimes one algorithm only works slightly better than another, and we want to see this difference. In contrast, if we look at the precision at the 10 documents, if you look at this whole set, well, what's the precision? What do you think? Well, it's easy to see that's 4 out of 10, right? So that precision is very meaningful because it tells us what user would see. So That's pretty useful, right? So it's a meaningful measure from a user's perspective. But if we use this measure to compare systems, it wouldn't be good because it wouldn't be sensitive to where these 4 relevant documents are ranked. If I move them around, the precision at 10 is still the same, right? So this is not a good measure for comparing different algorithms. In contrast, the average precision is a much better measure. It can tell the difference of difference in ranked lists in subtle ways.